Hey guys, how we doing? Today we're going to introduce the next section of what we're covering. It's circular motion and gravitation. So we're starting on page 96 of our yellow book here when you're following along, and we will be working some sample problems together, so you need to go through those. All right, so circular motion. We're going to call it uniform circular motion because in order for us to address the concepts, we have to say that we're moving in a constant way. So the way that we move is really consistent. So I can speed up and slow down in a circle, but that's not what I'm worried about now. What I really want to look at is if I'm moving in a constant speed around a circle. So that's what the word uniform means in this case. All right, so imagine you're driving a car and you have your steering wheel turned so that your car follows this perfectly circular path, and your speedometer is going to read 10 miles an hour. So this is an example of uniform circular motion. It's motion in a circle with constant speed. And as we travel around that circle, we're going to travel around its perimeter. And regardless of which circle we go, if we're moving in a circle, we're going to follow a perimeter. And our speed, let's just say it's 5 meters per second, then for every second, we're going to move 5 meters along that curved surface of your circle, right? So we're moving 5 meters every second around the perimeter of our circle. And one complete revolution, so one complete rotation, is going to be defined by our circumference. And our equation for circumference, as we know, is 2 times pi times the radius, or pi times diameter. It's the same thing. Should all be reviewed for me from geometry. So since our distance is our circumference, and circumference is 2 pi r, our velocity is also distance over time if we think back, or displacement over time. Therefore, our velocity, just by simple substitution, since our circumference is our distance, it's 2 pi r, and we plug that in here, we just substitute, so now we get our circumference is 2 pi r over t, okay? And t in this case is not necessarily time, but it is a time, but it's called our period. The period is the time it takes to complete one full rotation around that circle. So we completely cycle around that circle, and the time it takes is the period of our motion. Oops. So period is measured in seconds. So it's going to be the time it takes for us to go fully around that circle. So in my circle, if it takes me 15 seconds to go from the top of my circle all the way back around to the top, our period is 15 seconds. And our frequency is the number of cycles per second. So if I go 10 times around that circle in 1 second, then my frequency is 10 hertz, which is just revolutions per second. So it helps us to know that period, t, and frequency, f, are the inverse of one another. So if I divide one by its inverse, then I'm going to find the other. So the inverse of time, or the inverse of period, is frequency. And you'll see that at work in just a minute. So here we go. Our first sample problem on page 96 is 4.24. So a car travels 125 revolutions per minute around a track that has a radius of 30 meters. So our first thing we're challenged with is finding the period. Okay, and if you remember, the period is the time it takes to complete one full rotation. So we know that we cover 125 revolutions for every minute, and we also know that there are 60 seconds in 1 minute. So I can rewrite that as 125 revolutions over 60 seconds. We do the math, we divide them out, and we get 208 revolutions, 2.08 revolutions per second. So that means, in order for me to, that means that we go a little more than 2 complete rotations every second. So that, if you recall, is our frequency. That equals our frequency. So our frequency of rotation is 2.8 revolutions per second. That's how fast we go around there. So knowing this, we can find the period, because remember, the period is the inverse of frequency. So that's what we have here. So our period, t, is equal to the inverse, or 1 over our frequency. So all we do now is we substitute this into that equation. So 1 over 2.08. So our period is 0.48 seconds. So it takes 0.48 seconds to go one full rotation. Right, and that's what our answer is. our second part of the problem, we need to find our velocity. Okay, and if you remember back to a few slides ago, we had the equation for velocity, or we were given here 0.48 seconds and 30 meters, and this is our equation for velocity around the outside of that circle. So our velocity is 2 pi r over our period. We have our period from the previous question. So we go 2 times pi times our radius, which is 30, over 0.48, and it gives us 125 pi, or if I do the multiplication, it's roughly 392.7 meters per second. Okay, and there's our answer. So we have found our velocity. The car, so we would say that our car has a tangential velocity of 392.7 meters per second. And we'll get to what that really means on this next slide. Tangential velocity. So the word tangent means it's if we were to draw a line that touches only one point in a circle, then that would be a tangent line. So it's the straight line velocity at any point on the perimeter of our circle. So if we're going in a circle, it's going to be what our speedometer reads. That's going to be our tangential velocity. If I were traveling in a circle, as my speedometer reads, we just said that. Okay. So the direction of our velocity vector is the tangent line to that circle. And my picture here, this is is the circumference of my circle, and this V is the tangent line to that circle, and that V is my velocity vector. All right, same picture again. So if our speedometer reading were constant with a car moving around the track, would our car's velocity be constant? Why or why not? So this question might be a little confusing, but what do we know about velocity? Velocity is a vector, right? And the difference between a vector and a scalar is that vectors have both magnitude and direction. So is my car's magnitude of my velocity changing? No, because my speedometer reading is constant. But is my velocity changing for some other reason? Yes, because my direction is changing. Anytime I turn, I'm accelerating. I'm changing my velocity. So the magnitude of our velocity is constant, but the direction is constantly changing. Since velocity has direction, it changes. Our velocity is never the same. We're accelerating here. So what does that mean about this acceleration? We've got, whenever our object changes directions, it accelerates. And we call this acceleration centripetal acceleration. So you've probably heard centripetal force before, and we'll get into that in just a minute. And centripetal, the word, if you break it down into its original Greek, maybe Latin, I don't know exactly, it means center seeking. So that means that this acceleration is always toward the very center of our circle, always. So we've got a picture of it here. This is our tangential velocity. Here, they follow tangent lines to this circle. And then our acceleration, as you can see, is always directed toward the center of my circle. Okay, just a little graphic there for you. So centripetal acceleration, again, is given by the equation, it's on here somewhere, where r is the radius and v is the tangential velocity, and our acceleration, hang on, right here. Here's our equation, this is what I'm saying. So our centripetal acceleration equals our tangential velocity squared divided by the radius, okay? And there's a derivation for this, but I'm not really concerned with showing you how to get it. We just need to know that that's what our formula is. And this acceleration is always perpendicular to our tangential velocity. So perpendicular to a tangent line means directly toward the center of that circle. So now we're in our yellow book on page 97. So we now have a car moving at 10 meters per second, and it takes a turn around a circle or a curve with a radius of 25.0 meters, and we're going to determine its centripetal acceleration. Okay, so we go back to that last slide and we pick up our equation, or we write our givens first, excuse me. Our velocity is 10 meters per second, our tangential velocity is 10 meters per second, and our radius is 25. And we take that equation, we know that our centripetal acceleration equals our v squared over our r. So simple, we plug it in. Our v is 10, and our radius is 25, so 10 squared over 25. And we get 100 over 25, and our answer is 4 meters per second squared. So our centripetal acceleration is 4 meters per second squared. So we're always advancing toward the center of that circle at 4 meters per second every second. All right, centripetal force. So this is the one I'm sure that you've heard of. And centripetal force is this inward force that we have to apply to keep moving in a circle. So without this, no motion can occur. So a good example of this would be like a ball tied to a string that you're spinning. If I'm spinning a ball tied to a string, then what is the agent of the centripetal force? The string, because the string pulls that ball toward the center. So that's what causes our centripetal force. Without this, things are going to keep going in a straight line. So if I'm spinning that string and then I cut it, then instantly that ball is going to shoot off in a tangent along the direction of its velocity vector, tangent to the circle it was once in. So from Newton's second law, and we can substitute the equation for centripetal force. Then centripetal force equals mv squared over r, and I'll show you Tuesday if you want to know how we got this. So our centripetal force equals mass times velocity squared divided by our radius. Another fairly simple equation. Not going to have to do much derivation here. And a good example, another good example of centripetal force would be a roller coaster. So we've got a roller coaster here, and we travel along this track. So in this case, the track is the agent for the centripetal force. So the track causes that center-seeking acceleration, and the only thing that keeps us moving forward is our inertia. So if this track were to abruptly end right here, then what direction would not what direction, but the direction that this train would follow would be along this line, this tangent line to our circle. So that's a good example. Another good example is of centripetal force is the gravitron ride at the carnival, the one that makes you throw up all the time. It spins in a fast circle. That's a good example. So the ride pushes you toward the center, and that's the agent for your centripetal force. All right, guys, and what I'm going to require of you to do now is I'm going to require you to do the sample problem starting on page 97, and so 4.26a through 4.29, or actually through 4.30 on, these are out of order. So page 97 through 100. I think I did this right. Okay, well your book might have a small error on it. If that's the case, then that's fine. So actually, oh, I see what we did. So page 97, 98, and 99 through problem 4.30. All right, and I think that's it. All right, thanks a lot, guys.